Right, guys. Thank you for still coming. I think I have tortured you quite a lot, and fewer numbers are showing up. So I finished holding you. Now I'm going to pester you. We are talking about limits in metric spaces. So first we need to define, and that's part of the reason I introduced the p-norm, is you will have to learn abstract open sets, open ball, all those things, and this will give us some intuition on how those structures might look like in different metrics. So we make the following definition, and if we have a metric space MD, so you remember that just means that we have some set and a distance function defined on that set, we define the following sets. First set is going to be called BR of X, and that's the set of all Y that belong to M, such that the distance between X and Y is smaller than this R. And here, of course, we have R is bigger than 0, and X is just a point in M. So this is known as, so this is open ball of radius R. Okay, thank you. Open ball of radius R, that's one definition we make. Sometimes we will use this definition, so we would say that the ball of radius R with a bar on top of it around X, this will be the set of all Y in M, such that the distance between X and Y is no greater than R. And this is known as the closed ball. Of radius R. Now, do you see why we call them open balls, closed balls? Well, really this means this is the radius with the center at X. So in Euclidean space, if you draw this, the picture of the ball where the metric is Euclidean, this will look like a disk. And this will look like a disk together with the boundary circle. Okay? We will see pictures of that. So we have open ball and the closed ball of radius R. So now let's see examples of how such structures will appear in different spaces. So suppose we take as our example the set R. When I say R, I mean, of course, the absolute value metric. So then the ball of radius R around X is simply an interval, since we only have a one-dimensional disk. So that means this would be X minus R x plus r. That's our ball. And the closed ball around x will be simply the closed interval x minus r, x plus r. That much is clear. B, in R2, so this structure is a disk. Of radius r centered at x. Now, in general, let's consider what happens. What are those structures if we use different metrics, right? So let's consider what happens. So this two node, this in R2, when I say it's the disk, I mean that I'm using the structure R2, and I'm using the 2 norm. That's your usual Euclidean measurement of distance. So that means, of course, that if I want to measure the size of x in the 2 norm, that would be root of x1 squared plus x2 squared, where x is simply the vector x1, x2. Okay. Now you might wonder, how in general do we visualize p norms? So see, how would open balls for simplicity, I'm just using R2 and I'm using the metric P look like? Okay. So easiest, I think, is if I just turn on the projector. Hopefully it works, and I'll just show you pictures. That constructed before. So, and try to see why that is the case. Okay, and I'll give you at least one example of where I use this idea for some purpose. Okay, right? So you see, this is the 1 norm. Okay, so let's see what happens if I just have the 1 norm. This will be the outline of the disk. So if AB is the point x at which it's centered. Okay, so x is the point AB. That's the center of it, and it will look like a tilted square. Why would it look this way? Well, think about the boundary. Think about this line. What is this? Right? So this line is exactly where the distance is equal to 1. Okay? So the line on the side if you just look at one segment of it, then what is this line? This is the line where the norm of x is equal to, I drew it for radius 1. So this is a ball of radius, or if it's radius r, it's going to be a parallel line. So if the size of x is equal to 1, what does it mean? It means that absolute value of x1 plus absolute value of x2 equals 1. Now in the first quadrant, absolute values can be dropped, and this becomes just, or better, if I, instead of using x1, x2, let's just say that this means just x, absolute value of x plus absolute value of y is equal to 1. Yes? Is equal to 1. In the first quadrant, that just means that x plus y equals to 1, and then you get this line. This is the line y equals 1 minus x. That's this line. Okay? If in general, if it's ball of radius r, this is just x plus y equal to r, and that means just y is equal to r minus x, so it has the same slope. This will be a parallel line, either farther out or closer in. Okay? So you get, and then if you consider the absolute value in other places, so in this case x is negative, so you multiply the x-axis by minus 1, right? So it will be minus x plus y equal to 1, and this will be this line, this will be that line, etc. Okay? So it will look like this picture over here. That's the shape of the one norm open ball. It doesn't look like a disc at all. Naturally, if you use the Euclidean norm, this is if you use the norm 2, then you get a disc. Outline of it is just a circle. Now, if you begin increasing p to higher degree, so p is bigger than 2, it starts looking like a rounded square. And as you push p to infinity, it becomes exactly a square. Right? It becomes exactly a square. So the open ball looks like a square. And this is known as the Manhattan metric. So in Manhattan, when you calculate shortest distance, you cannot just calculate the Euclidean distance from one point to another, because you have to go along avenues and streets, and therefore you have to take orders. So then you might use the supremum, or the max. In this case, supremum and max are the same. Use the sup metric. And that is when p goes to infinity. Here is the animation of all of it happening, so the transformation happening from p equal to 1 onward. So this is how it would look. Okay, so this, as you see, this is the p-normed ball, where p is equal to 1. And then this is what happens when p gets bigger than 1, you see? It's at some moment it begins to widen, eventually becoming a circle, and then widens further. And it's becoming, as you see now, it's becoming slower and slower. With bigger p's, the difference is less and less visible. But at infinity, farther than this video can show, you see this happened. I mean, I pushed it to infinity, it became a square. Of course, the video would run forever before you see it becoming a square. Now, one example of where you apply this type of things, when you just need to change norms, one example I used it for is, let's see, if I can find it. All right, so I had a student a while ago, and he gave me, maybe you're familiar with this engineering problem. I'll show you maybe in a separate YouTube video what that problem is. Bicycle with square wheels. So he was interested in constructing a bicycle that has square wheels, right? So that's an example of that. And this bicycle, of course, you cannot start this bicycle on such a ramp, but let's see. Here, right? You see that the idea is you have a bicycle with square wheels, and you need to design a road on which the bicycle will go, okay? So he asked me, it was in Calc 3, he asked me if I could help him understand this problem, and I came up with a mathematical equation. And just to check that I haven't made some errors, I just simulated it here. Okay, so that's my square wheel. Okay, so what did I have to do? In principle, that's why you see. That's why I needed to use different norms. What I did is I said, okay, so what is a circle? Very simply, a square is just a circle in the p norm, right? So I used p norm spaces for that immediately, right? So for different problems, different applications, you need different norms, right? Sometimes you want your open disk to be a square, sometimes you want it to be another shape. And with some proper metrics, it might be of the exactly right shape. All right, good? So we answered C, I guess, right? You can think about the different P's. You can kind of come up with an explanation of why it looks like a distorted circle. Why is it really beginning with a tilted square, and then it's becoming a circle? That has to do with, very simply, with distortions. You think about how a p power will distort space, and you can think that this will be the effect on the disk. All right. So then let's consider D. How would we visualize in one of the simplest metrics, but I would argue a little bit more interesting than it seems on first glance. So we have discrete space. Do you remember what's a discrete space? A discrete space is where distance to anything is 1, anything other than the point where you're at, right? So the distance is either 0 or 1. So the distance from me to the stable is 1 unit, the same as the distance from where I'm standing to my house. Right? So in this discrete space, can you tell me how would the open ball of radius 1 around X look like? How many points will it include? So this means the points that are a distance of less than 1 away from X. What are those points?
4 points. No.
I'm sorry?
4 points.
4 points? No. And it's in any space. I didn't give it a structure. It could be, you can assign this metric to anything, right? And that would be what? So the distance 1 unit away from this X. 1 unit. What's less than 1 unit away from where I stand? Only one thing, my position, because the distance is always 1 unit. Any other position where I'm not is 1 unit away. So therefore, it's only the point X. That's why it's called discrete, because this is going to be called a neighborhood, as you're going to see, right? So this contains all the guys that live next to him. When I talk about open sets, you will see why this is a good definition of a neighborhood. Okay? So this guy is, in some sense, alone. He's away from anybody else. Nobody understands him, kind of like I am. That's why it's my favorite space. And becomes more and more favorite over the years. So what we have is ball of, let's say, radius bigger than 1. Let's say ball of radius r around X, where r is, so here I'll write r bigger than 1 or equal to 1. That will mean what? No, so r just bigger than 1. R bigger than 1. The ball of radius r around X will contain what? Everything. Right? Everything, because what this means? This means a ball of radius r. So basically this gathers all the points that are a distance of, the distance less than r. But since r is bigger than 1, everything is a distance less than r. And that will be M, the whole space. Okay? Understood? So discrete space is going to be playing a major role. We're going to use it as a bunch of easy examples, easy properties. And it's important in connectedness. So D, E, if we have a norm vector space, V and this norm, ball centered at 0, so 0 is the 0 vector, okay? If you want to draw an arrow, so the balls that have the center around 0, they play a special role. And why? Because I can take any ball of radius r centered around the vector x, and that simply is x plus the ball of radius r centered around 0. And what is that? That is actually, by properties of vector space, this is just going to be x plus r times the ball of radius 1 centered at 0. Okay? So in other words, really, if I understand everything about ball of radius 1 around 0, I understand everything about all open balls. In particular, if you play a video, an animation, and you see that your open ball changes shape as you move it across, that might mean that what you have is a nonlinear space, because the ball, if it's a vector space, if it's a linear space, will have the same shape no matter where you place it on this infinite screen. Okay? So in other words, if I have a metric and in one region the open ball looks a little bit like a square, but if I push it somewhere else it looks a little bit like a star, then you know that this is not quite, this is not a vector space, not a norm vector space to be precise. Good? So that will happen with a bunch of metrics when you have different distortions in different areas in space. So norm vector space means you have the same distortions everywhere around the space. All right. So now, why did we need open balls? So this allows us to describe some basic geometric concepts such as boundedness. That's the first thing we're able to describe by it. So we have this definition, and you will say that a set A, it's a subset of M, is said to be bounded. So it means it's not infinitely stretched if A belongs to the ball of radius r around x for some x belonging to the space M, and r which is just bigger than 0. So bounded means that I can contain it inside of a bubble. So I can blow up a big enough bubble and it will contain that full subset A, and then it's bounded. So exactly which x and r doesn't really matter. If you find one x and one r, you will find plenty of others. You can just, in fact, if you find one x, you can then shift it to any other x in the space and just change the radius appropriately. That can be easily established. So you can also notice, so you can say that A is bounded if and only if the supremum of the distance of points x and A is less than infinity, and the supremum is taken over all A in the set A, and x is any element in M. So in other words, what I can do is, if I fix some point x somewhere in the space, and I measure the maximal, the biggest distance from x to any point A. The supremum, because there might not be an actual biggest distance, but there will be a supremum, right? And if I find that the supremum is finite, then I know the set is bounded, because the supremum can be taken as the radius of my ball centered at x. Okay? So we then can define the diameter. So diameter of A, that would be the supremum of the distances between any 2 points. So that would be supremum of distance AB, where both A and B are elements of the set A. Okay? So this just means that I just take 2 points in A and I measure the distance between them and I find the farthest 2 points away from each other, and that will be the diameter of the set. And then, in definition, this will make more sense when we talk again about open sets. There is this word neighborhood. Of X. What this means is any set containing an open ball about X. So that means a set, and there is an open ball centered at X. Later on, you will drop this assumption almost exclusively when you talk about neighborhoods. You actually mean that it's already the open ball. It's a synonym to the open ball. Okay, and yeah, so that means all the points in your immediate vicinity of radius r. So that gathers all the points that are r units away from you. So in a way, that's your first preliminary understanding why it's a neighborhood. It gathers all the points that are within a radius r from where you are located. Okay. So this means a thick collection of points around X. Kind of. Intuitive.
So is closed ball automatically a neighborhood of an open ball?
Yes, closed ball will be so neighborhood of a point, right? So the language is closed ball is a neighborhood of a point that is the center of this closed ball. But this is going to be unimportant. You see, I never actually, when I say neighborhood, I never mean any set. I will always mean an open ball. It's just some people mean this, okay? But usually, as you go on, it becomes, as far as I noticed, unimportant that it's just any set. What matters is the open ball. So a neighborhood, just another word for an open ball for now. Okay? And then finally, we can now talk about convergence of sequences in the metric M. So that's the first thing. So definition. So you remember what the sequence is. So if I take the sequence xn, so a sequence of points, really a sequence is a function from the natural numbers, 2 elements in M, some of them, right? Really, again, you can think of it as just a list of elements. So I take one point, and I take another, and I take another, and I can say that this sequence converges to a point x, to a point x belonging to M if the distance between xn and x goes to 0, where this distance again is now a sequence of real numbers. Notice the distance is, thank you so much, it's very thoughtful. It seems, yeah, so you understand what this definition means. So you will see that the distance between the xn will go to 0. And that means that as you delete initial elements in the sequence, as you delete x1, x2, x3, eventually all of them are really, really close to x. Okay, so what it means, so maybe I will write notice that the distance xn x, where n is 1 to infinity, is a real valued sequence. That goes to 0. Yes, it's real valued because distances convert pair of numbers to real numbers. So this is just a real, basically talking about convergent sequences always translates to talking about real sequences converging to 0. And I will say what it means to converge to 0 more precisely. So in particular, what this means is dxnx goes to 0 if and only if for any epsilon bigger than 0. You remember that stuff, right? Epsilon. For any epsilon bigger than 0, there is n, which is going to be n of epsilon. N is really a function of epsilon, such that little n bigger than or equal to n of epsilon implies that the distance between xn and x is less than epsilon. What this n means, in other words, it means, I will try to show you a picture of what it is in a second. So, actually, first let me write all the various definitions in terms of open balls. So for now, what this means is that what you have is if you select a very, very small real number, positive real number, you can find the tail of the sequence. In other words, just delete some of the initial members of the sequence, and then the ones that remain, all the infinitely many elements of the sequence that remain, they will be within epsilon away from x. I will show you a picture of that so you can really see. Okay? So this involves delta epsilon, and sometimes this is not a convenient, not very generalizable if you go to study topology. It's not, distances are sometimes hard to work with, but you can define open, or you can define neighborhoods. So that means, what does this mean? This means that xn goes under the metric d to x if and only if xn is eventually in a ball of radius epsilon around x for any epsilon bigger than 0. Okay? And what this means in essence that xn is eventually in any given neighborhood of x. So you understand how you think of eventually. So that means that, let's say that I select the radius to be 1 over a million, right? So it's very small. So within a million of a distance, and then I notice that starting with, let's say, the subscript 100, all the terms of the sequence, x sub 100, x sub 101, etc., they are all within that radius away from x. So then n of 1 millionth will be 100. That's basically the first instance when I begin seeing the xn's in that particular neighborhood. But what will happen, whatever radius I select, eventually by just deleting a few of the initial terms of the sequence, all the others are going to be within an open ball. Okay? If you haven't understood it, I will show you a picture. Now, perhaps you already dealt with convergent sequences, but perhaps you don't know what's a Cauchy sequence, do you? So you can say then the following definition is that the sequence xn is Cauchy if for any epsilon bigger than 0, there is an n of epsilon such that the distance between x sub n and x sub m is smaller than epsilon whenever n and m are bigger than or equal to n of epsilon. Okay? So what is this Cauchy thing? Let me try to explain with a picture. So here is what's going to happen. Okay, so this is going to be a similar picture for convergent sequences as well as for Cauchy sequences. So imagine that the elements of your sequence are unts, and for the purpose they are frozen in the frame, so they don't move, right? So you took a photograph of the ants, and you're presenting a token about them, and what you observe is the following, right? So you observe that that you see a few ants scattered around in the space, but somewhere you see they're clustering. The population of ants is really densely packed. Okay, so what is happening? Where are they densely packed? So what you can do is you can imagine that you can go somewhere in space, somewhere, and you can draw a target, and the target can be made small, as small as you like. I can shrink it. Okay, so I shrunk it to a particular radius epsilon. Epsilon is, let's say, maybe a very small number. So I shrunk it for that epsilon. So let's say this epsilon in this case is equal to 1. Let's say it's 1 or whatever, 1 micron, I don't know, 1 centimeter. Let's say 1 centimeter. So I crunched it with 1 centimeter, and then I observe the following. So you observe that if I label the ants, I see that ant 1, 2, 3, 4, all the way to ant number 10. They are outside of this circle, but every other ant, and again, there must be infinitely many ants, and more so, the ants are 1 point. They are not, in this discussion, they must not occupy any width. Okay? So what you observe is that all the other ants are within the disk of radius epsilon equal to 1. Okay? So you don't observe that they cluster around a point. What you observe is just they are like in a train, they're crowded next to each other. That's what Cauchy sequence is weaker than convergent sequences, because convergent sequence means I can zoom in, and maybe it's a sugar cube. They're interested in a sugar cube, and that's why they're clustering. So X will be the sugar cube around which they cluster. That would be convergent sequence, okay? And if you don't see what they cluster about, you just say it's a Cauchy sequence. So that's what this definition is signifying. It means that the elements are becoming densely packed next to each other. Yes?
Why does the sequence? Does the sequence go towards a certain point as the n gets bigger?
It does not. All I'm saying is that I might need to shift the target. I might have to shift it between one ant to another. It might not be focused anywhere. What I'm just saying is that somewhere in space, focused around the ant. In fact, I can focus basically I will change my focus in this case, this n sub epsilon. What is n sub epsilon in this picture? So where epsilon is 1. What is n sub 1? Can you tell me in the picture? It's a function of epsilon. In other words, when I say n, I will need to shift, depending on the epsilon, I'll need to shift the target. Okay? So epsilon specifies the size of my target. Okay? So this target is the disk. And where the disk is focused, that's the center of the disk. Okay? Make sense? So n sub epsilon, you control two things. So what you have to do is you have to, epsilon will tell you how big is the target, and n sub epsilon will tell you where to focus the target. Where do I focus my target in this picture? What's n sub epsilon where n is 1? So comprehension check. what's n of 1, as I do in the picture? What is that? Yes?
11.
11. Wonderful. It is 11. What does the 1 refer to? The 1 refers to what?
The size of the target.
The size of the radius of this target mark. So it's this line or this line, right? They're presumably the same, at least in that picture. Make sense? So what is n sub 1? This is the 11th ant that I place my target on, right? Now, in this picture, obviously, I didn't have time to draw infinitely many ants. If I had more, I would have. But, you know, so again, it's just an analogy, okay? Make sense? So in this case, I will have to shift my target from one ant to another. All that matters is that all the other ants will be within target. In fact, this is saying what? This is saying that not only do I need to place my target here, but in fact, I can place it on any m, where m is bigger than this guy. And if I don't change the size of the target, I will find that all the ants saved for just the ones that are here, say in this case up to the 10th ant, all the others are within the target. And you see, this is not a full picture. This does not prove it's Cauchy. This only shows you that that it clusters to within one radius, but it has to continue to cluster arbitrarily densely. In other words, I will change epsilon to any number, no matter how small. That makes my target very small, and I cannot contain many ants. So more ants will have to be deleted, but eventually, all but finitely many of the ants are going to be within this target. Does it make sense?
I guess a better question would be, okay, say n of 1 is 11, right?
Right.
Why doesn't ant number 12 decide he doesn't want to be part of the crowd?
Well, they're not moving, right? So because then you have a Cauchy sequence in time, so then you have to consider time. So you can simulate that as well, but that's a metric space that contains space and time. So, and you have different sequences as a function of time as well.
But why does ant 12 not start next to ant 2 or something? Why do they all...
Well, it's just a picture to illustrate the concept. So I do not know what the ants are doing. I'm just saying they're clustering somewhere in the picture.
Why are they clustering as
that's
the
that's a theological
increase?
question. Why do they cluster, right?
As the numbers increase, though. That's the thing, you know? Like, why is that ant number 1 and not ant number 24? You know, like,
well, I mean, a sequence naturally is how I labeled it, right? I labeled a sequence, I needed to label, this is an element of space. Really, it's not really an ant, rather than it is in this case maybe a point in R2. So this is one point in R2 that I picked, this is the second point in R2 that I picked, and I picked a bunch of points in the two-dimensional space. And I see that those points are clustering somewhere. So in other words, the points are sparse in many places, but somewhere I see that I have a lot of those points. And I zoom in where I have a lot of those points, and I see that most of them are contained in some region. And it gets denser and denser, you understand what I'm saying, right? If you shrink the radius, you see that infinitely many of them are inside of a very small disk.
So you chose to order them that way.
Of course.
That's how you chose to order this. That was my question.
Right.
If there's...
So you pick a sequence. When you take elements in M, you are ordering them in a particular way.
So that it makes sense that as n gets bigger, they'll cluster in a certain...
It's happening only in special cases. You can construct plenty of sequences that don't.
That's
so for example, the integers.
Yeah.
Integers don't cluster at all, right?
Yeah.
1, 2, 3, 4, they are discretely separated. Right? So the sequence 1, 2, 3, 4 in regular metric R does not cluster.
Yeah.
Okay? We're going to play this example with different metrics and see does it cluster using this metric or does it. Okay? Make sense? Alright, so again I'll turn off the projector since I don't have much room. And you see that this is more general. So in Cauchy sequence, I'm just describing that the elements of the sequence cluster, but I don't claim they cluster close to one point. We're going to prove that in a moment, right? So do you have an intuition? Convergent sequence. Will a convergent sequence be Cauchy or not? A sequence that converges. So in other words, I have ants, and in fact I see that they are interested in the sugar cube. So they are close, most of them, all but finitely many are close to a sugar cube. It's a convergent sequence, they converge to the sugar cube. Is this sequence a Cauchy sequence or not? Yes or no? Shake your head like this if you think it's Cauchy. Yes? It is Cauchy because in particular they cluster about one point. But a Cauchy sequence is just saying that they're just gathering there for no reason, like in traffic. Suddenly you are stuck there and you have no idea why. There is no reason. There is no accident. There is no police that you can see. It's just no reason, but they cluster there. Okay? So we'll see examples of Cauchy sequences in a moment. So another way of saying it's a Cauchy sequence, notice that what this is equivalent to is saying that the diameter of the sequence xn, where n starts at n epsilon, to infinity is less than epsilon. Okay? In other words, the diameter can be made arbitrarily small by deleting a bunch of terms of the sequence, by starting to look at the sequence not from 1, but maybe from a bigger number. All right. So I hope I made it clear that that convergence is in M. So I'll write this definition again, so you can compare it. A sequence xn, which is a subset of M, converges to x belonging to M if xn goes under the metric D. So M has a metric assigned to it. Under the metric D, xn will approach the point x as measured in terms of that metric. Okay, so two things that you have to observe. Convergence requires that I take point in the space M, and I say it converges in M if the element actually is something that is part of my space. It has to be part of my universe that you cluster about. And it is also relevant to mention the distance, because possibly convergence might be distance specific. For one distance, convergence doesn't happen. For another distance, it might. So let's see examples, okay? And pay attention to M. So let M equal to the interval from 0 to infinity. And it's equipped usual metric. So that's the absolute value, okay? So then we pick the sequence 1 over M. So that's a sequence in M. So A is 1 over N convergent. Is it convergent? Answer is, what's the answer? The answer is yes. So this is example A. Is it convergent? And make sure that you are able to justify it. So the answer is yes, because 1 over n minus 0, if I take the absolute value, this approaches to 0. Okay? Where this 0 is just the 0 distance, and this 0 is the point that I have right here. Okay? So we have convergence. Okay? Is the sequence Cauchy? Is it Cauchy? Yeah, of course. If it converges, it should be Cauchy. It means what? It means those are the ants, right? The ants are 1, 1/2, 1/3, 1/4, and you see that the ants are clustering around 0. Okay? So, yes, and why is it yes again? We're going to show that, we're going to prove a proposition where you don't have to bother too much, but yes, It's Cauchy because you can take 1 over n minus 1 over m, and that will be made, that is less than epsilon if so if n m are sufficiently large. How do I know? Well, I use triangle inequality. Okay? We know that as n goes to infinity, that's what's sufficient large. So its distance from 0, 1 over n distance from 0 is disappearing. That's because what I can do is I can say that 1 over n minus 1 over m. By triangle inequality, this is less than or equal to 1 over n minus 0 plus 0 minus 1 over m. And this will go to 0. Right? So this, if I take n large enough, and this, if I take m large enough, right? I will make them really small. I'll make them less than epsilon, the sum of them together. Okay? So take n so that 1 over n, its magnitude is less than 1 over 1. Basically, so this magnitude is less than epsilon over 2, and that it works. Okay? So this is example A. It's in some way trivial. So now you understood what I mean. So you make this less than epsilon over 2, and this less than epsilon over 2, which you can easily do by the Archimedean property. So in this case, let's consider what happens if I take, so this will be B. I take the same sequence, but I'm going to change the metric. Okay, B. So now,
Excuse me?
yes?
So by the definition, right, it
Yeah.
says whenever n and m are greater than some number n of epsilon, right?
Right.
Does that have to be a finite number?
Yes, it has to be a finite number.
So does that mean it's a finite number such that 1 over that finite number minus 0 goes to 0?
No, well, okay, so thank you for mentioning it. Maybe it was, again, I think, my God, I made a lousy explanation of it, just a kind of hand-waving explanation of it. So here is what I mean, okay? So what I do is this. I take 1 over n minus 1 over m, and this is less than or equal to 1 over n minus 0 plus 0 minus 1 over m, which I can also write as 1 over m minus 0. And then because 1 over n and 1 over m are positive numbers, so this is just 1 over n plus 1 over m. Okay? I just eliminate the absolute value. And what I will make, I will make the first guy less than epsilon over 2. The first guy will be made less than epsilon over 2. And the second guy will be made less than epsilon over 2. So, and then this would be epsilon, it works. So what I mean is, what is n of epsilon? N of epsilon, in this case, for the Cauchy sequence, n of epsilon will have to be, in this case, will have to be n such that 1 over n is less than epsilon over 2. Okay? So that's the n of epsilon, right? This is n such that 1 over n is less than epsilon over 2, and that is the same thing as requiring capital N to be bigger than 2 divided by epsilon. Okay? So what it means, in other words, is suppose that what I want to. So what you do is you have the target, and you specify epsilon for the target. Then I need to calculate what's 2 over epsilon. So if epsilon is, in particular, if epsilon is equal to, so if epsilon is equal to 1 over, let's say, 20. Okay, that's a particular epsilon. 1 over 20. Then n has to be bigger than 1. So n has to be bigger than 2 divided by 1 over 20, and that will have to be 40. Okay. So what this is saying is, suppose that I want to see the ants 1 over n cluster together, right, without reference to 0. So I say what you do is pick the sequence starting with 1 divided by 40. Okay. So 1 divided by 40, 1 divided by 41, etc. So if you take any of those two elements, you take the absolute value of their difference, you will find that the distance will be less than 1 over 20. Okay? And for a different epsilon, the number n will have to be higher. So remember what Cauchy sequences mean, it's a little bit of a dynamic concept. You specify your epsilon, and for that epsilon you need to tell me how many terms I delete, so that the rest are clustered together within that target of size epsilon. Make sense? So what you say, so the target will be squeezed, but what you do is you first squeeze the target and then tell me, is there a procedure to delete finitely many of the ants, so that the ones that remain will be within epsilon from one another. And if it can be done for any epsilon, as this procedure shows it can be done for any epsilon, that means the sequence clusters arbitrarily densely. Which you know already because it clusters around 0. Notice we use 0 as the point of cluster in showing that it's Cauchy. Okay, good. But the important part here is, so this you might have known from other courses, but here we are now going to change the example. So now B. So M is still, as we had before, 0 to infinity, but actually M will be changed not to include 0. So I'm actually going to not include 0. Okay, 0 is missing. And the distance between points x, y will be computed by the internal method. So what I do is I take 1 over x minus 1 over y, and I take the absolute value. And you remember that 1 over, it's an injective map. So that works, right? I can take all those points. That's why I have to exclude 0, so that I take 1 over that number, and then I measure distance this way. Okay? By internal method, this is going to be a distance function. So in this case, question is the sequence convergent? Is this a convergent sequence using this metric? What do you think?
I want to say no just because the first one was convergent, but
So only psychologically, right? What about reasoning? Do you have a reason why you think it's yes or no? Is it convergent or not? So let's see what happens if I just calculate distance between two arbitrary points. Well, let's see if I take distance between 1 over n and 1 over m. Okay? So I just took two members, two ants. I looked at their position and I measured the distance between them. What is that going to be?
1 over ant minus 1 over n.
So it ends up, if we do it quickly, it ends up being a distance between what? It ends up being a distance between, so what you do is, don't be confused, what do? You take this input and you place it here. So you take 1 over n.
So n minus m.
So it's n minus m. N minus m, and this is, in general, this is bigger than 1 if m is not equal to n. Okay, so what it means is that the distance, this distance, right, this is the distance. It is always, if I just look anywhere, the distance between any two of them is pretty big, it doesn't shrink. So the answer is not convergent and not Cauchy. To converge, they will have to, the elements have to get close to one another. Okay, so this is not convergent. Not Cauchy, and therefore not clustering. So we will prove it rigorously in a moment, but you see, if it converges to a sugar cube. That means it clusters to a sugar cube and therefore clusters next to each other. But what I see is that the ants are not even close to one another, so how could they converge? Not clustering, and that implies not convergent. Make sense?
So in the first example, when you said let n be from 0 to infinity with usual metric, by usual metric,
Absolute value.
Do you mean the absolute value of n minus m?
The absolute value of 1 over n minus 1 over m. If I measure this, so this usual metric, 1 over n, you see that the numbers 1, 1/2, 1/3 all live in the positive segment of the non-negative segment of the real numbers. Yes? So in this case, this would have been this is a convergent sequence under usual metric, and it's also a Cauchy sequence.
So what's the difference between this example and that example? Just that
They
we're
have
not
a different
including
metric.
0?
They have a different metric. They have a different metric. It's metric 1 over x. The geometric effect is in fact if you place a spherical mirror. So what you have is those sequences that cluster to 0, they are now clustering to infinity. And therefore, in your usual sense, they're not clustering. They will cluster again on the Riemann sphere. Okay, so there are all sorts of notions. But really what it is, it's like, you see, between 0 and 1, 0 and 1 is like a reflection through a spherical mirror of radius 1 of the interval 1 to infinity. And therefore the sequence is 1 stays at 1, it doesn't change, 1 over 1 is 1, and everything to the left is moved to the integers to the right. Okay?
Can you define the distance in that one without just using usual metrics like distance?
Well,
from
when I
X
say
to
usual
Y?
metric, it's absolute value. So the distance, it means with usual metric, so it means that I'm using here m absolute value. Okay? So the usual metric is just absolute value. Make sense? Guys, your eyes are bloodshot. This is easy, right? Makes sense. What you do is you play with metrics, and what you have to understand that depending on the metric, it will be a different statement. Not only on the metric, but also on the space. So I'm going to ask the same question, again, the same easy question for the harmonic sequence. Yes, what do you want to say?
Isn't that like, is the Cauchy sequence then, as long as m and n increase, for any m and n, the distance function decreases?
The distance function of them should decrease, that's right. But eventually, not necessarily just strictly decreasing, but eventually becoming smaller than a number. Decreasing means only a monotonic thing. It can go up and down, but then it will eventually not be going back to where it used to be. Just the distances between points shrinks. Okay? But also remember that Cauchy sequence in what space and by what metric do you measure the Cauchy sequence? Because it was Cauchy using the usual metric, and I changed the metric, it's no longer Cauchy. Now I'm going to ask the same question back to the, I'm going to just say that this is my space, but I'm using the usual metric. And then you're going to tell me, does this converge or not? Is it Cauchy or not? Okay? So, C. So let M be the open. So I'm not using, I'm not allowing 0. So 0 to infinity. And distance between x and y is usual, so that means just absolute value x minus y. That's the default metric on R. Okay? So I'm going to ask, so 1 over n. Is it convergent? And when I say convergent, you have to now remember relative to M, or in M. Is it convergent? The answer is no.
Because 0 is
Because it wants to go to 0, but 0 does not exist in that space. So from the perspective of the space, you see the ants crowding around nothing. It's of course it's somewhat arbitrary. It's a wrote up, it's a made up example, but that's what happens when you have a non-complete space. Is that you see clustering, but not about anything. So no. So why not? Is that we can see that one over n minus x. So this is just this x is a point in M will be so maybe I'll draw it. Okay, so I'm trying to be somewhat, it's obvious, but I'm trying to be somewhat rigorous. So could it go to any other point? It wants to go to 0, you would say, but here is a point x. Could it possibly go in the metric to the point x? So let x belong to M. So x is not 0. And what we can do is we can take, somewhere here a cut. So this will be 1/2 x. Okay. So what you can say is that the answer is no. And how do I rigorously explain why no? For any x belonging to M, let epsilon equal to x divided by 2. Okay? X divided by 2. So this is the picture. So that's 1/2 x. Okay? Yep.
Does this count if n equals m?
Well, n equals m. That means that the distance between the point in itself is 0, but that's trivial.
Yeah, but there's no 0, right?
Again, to converge, it means that the sequence. Conversion means I delete a bunch of those sequences, and if it converges to something, to some x somewhere in the space, then if I delete finitely many terms of the sequence, the rest are going to cluster around this x. That's what convergence is. Okay, they have to cluster around this x. So you see, you naturally think, well, 0 is where they want to cluster, but 0 is not available to us. So then, if we just don't know about the existence of 0, we're not aware that 0 is even something, so we're going to look at the sequence and say it doesn't converge. How do we show that? We say, well, take any x. And we're going to show that whatever x we picked cannot be the point of convergence, and therefore it converges nowhere. So we let epsilon equal to x divided by 2, and then I can say let n of epsilon be equal to a number bigger than x over 2. So you take x over 2, and you take the ceiling. So you round it up, okay? Then what you can say is that the distance between 1 over n and x will be bigger than epsilon for all for all n bigger than or equal to n epsilon. Okay? So what I'm saying is start it with a number bigger than x over 2, and then 1 over n, all of them, all the 1 over n's, then are going to be very far away from this x. Okay? They're all going to be in here. What I'm really saying is look at the picture. You don't need to write it out so much. Look at the picture, right? So what I'm saying is you will see that eventually the sequences are gathering here. Right? So for any x, I don't have 0. You see that the terms of the sequence, they are going somewhere in that direction. And therefore, this is not a convergent sequence. You see, what I'm doing is a simulation. You might say, well, there is a 0, so of course, you know, it should go to 0, and 0 is not available to us, so therefore the sequence doesn't converge. Right? But what I'm trying to explain is in general, you might not be aware that there is something missing. You just see that the sequence doesn't converge, and that might be an argument by which you proceed. So look now before the last question. Is 1 over n Cauchy? Is 1 over n Cauchy? And the answer is yes, we've seen it before. Because it doesn't matter to 0, we saw that the distance between the two of them can be made small.
They're going into something.
So the answer, I will just write yes, we have seen this before, since you are so eager to leave me.
Let us go.
All right. So I suppose goodbye. I see I left you 3 minutes, and you ran away from me. You hurt me very deeply. Goodbye.